Okay, here we go. More fun with differentiability. So today we're going to talk about what it means for a function to be locally linear, and we're going to get a little bit of help from our calculator working through some of these derivatives. So first, for locally linear, the idea here is that we already know that taking the derivative of a function allows us to find the slope of a curve at a given point. So we've talked about how the derivative is just the slope of the tangent or the instantaneous rate of change. Okay, and this whole idea is based on the assumption that if we zoom in really close, that even the curviest of functions will look like a line. So to be differentiable at a point, to have a derivative defined at that point, if we zoom in, we should be able to see this locally linear behavior. Okay, and that's what we say. If we can zoom in and that function looks like a line at that point, we say that a function is locally linear. That it looks like a line in that really narrow region. Not locally line, locally linear. Okay, so therefore another way to think about places where a function does not have a derivative is that the function does not look like a line when you zoom in really close. And so we're going to see what this means in practical terms. So if we look at number 1, right, it says using calculators and graphs, determine if either of the following functions is differentiable at x equals 0. So if we look at the absolute value of x, right, we would assume that that's not differentiable at x equals 0 because we would assume there's a corner there. And so what I'm going to do is put this into my graphing calculator. So math num, here's my absolute value of x plus 1, and I'm going to graph it. And we see what we would expect, right, at x equals 0. We have that corner. But I want to see if I zoom in a few times, I want to see if I can ever get that to flatten out. So I'm just going to move my cursor right up by where that corner is, and I'm going to hit enter to zoom in. And you can see that corner behavior is still holding up. I'm going to go in a couple more times. All right, and maybe one more time zooming in, right on that corner. Right? That is clearly not straightening out. It's not locally linear at that point. So we would say for number 1 that it is not differentiable at x equals 0. So that supports what we already knew, right? Because of that corner at that point. So now let's take a look at number 2, our function g of x. So I'm going to go ahead and enter that in as well. So I'm going to go back to my y equals. I'm going to actually get back to my standard zoom. And I'm going to plug in x squared plus 0.0001 plus 0.99. So now I've got that in my calculator, and I'm going to hit graph. And we get a graph that looks really similar to what we got in number 1. It looks like that absolute value of x plus 1 function. So I'm going to do my test again. I'm going to start zooming in where that corner point is to get a better look at it. So it definitely looks like that corner is still holding up. So we'll go in a couple more times here. Still looks like a corner to me. But the more I go, I see that corner starting to round out. And so I can see it starting to flatten out, and I'm starting to see that locally linear behavior. So we'll go in one more time. And we can see there's a really clear difference between this function and the one we looked at before. So in this case, because it is starting to flatten out, it's becoming locally linear, we would say that g of x is differentiable at x equals 0. So that's the first concept we need to be aware of, that concept of local linearity. Now, we're going to look at what our calculator can do to help us calculate some of these derivatives. So we obviously have gotten very good at this point at finding derivatives at a point without our calculator. So for example, if I want to find the derivative of f of x equals 1 over x at x equals 2, right, my derivative notation, I know that the derivative of f at x equals 2, or f prime of 2, is the limit as x approaches 2 of f of x, 1 over x, minus f of 2, which is 1 over 2, over x minus 2. And so now I'm going to do some algebra to get rid of that fraction. So I'm going to multiply top and bottom by 2x. And so I have the limit as x approaches 2. When I distribute, on top I'm going to get 2 minus x. On the bottom I have x minus 2 times my 2x. So if I keep going, I notice that if I factor out a -1, I'll be able to get the same factor that I have in the denominator. So I'm going to factor out a -1, so I get an x minus 2 up top. I have x minus 2 times 2x in my denominator. Now I can cancel that factor from top and bottom, and I'm able to substitute 2 for x, and so my derivative is -1/4. So we have a means of doing that without our calculator. What I want to show you today is that we can get the same answer using our calculator. So what we do on our calculators, I'm going to get to my main screen here, is we use our nderiv function. So if you go to Math and then select 8, normally I'll just type it in, but I want to show you here. So Math 8, and you can see I get this notation. Now, if you don't have kind of that pretty math print type, I can help you in class, show you what the syntax looks like. The nice thing about this is it's really clear where I'm supposed to plug things in. So I'm just going to copy this. I get D, and then there's a box here. And then I have parentheses and another box. And then I have blank equals and a box. So here's what your calculator is looking for. In this box, it wants the independent variable, which for us, we're just going to use x when we're typing in these functions. In this box here, we're actually going to type in the function. And then this is going to be populated. That'll be our independent variable again. And then this is the value where we want to find that derivative. So if I'm using my same function here, my f of x equals 1 over x, when I type it into my calculator, it should look like this. The derivative with respect to x of 1 over x at x equals 2, because that's where I want to find my derivative. So I'm going to go ahead and type it in. You notice once I type in the independent variable, it populates this spot here. I'm going to type in my function 1 over x, and then I'm finding that at x equals 2. If I hit enter, I get a decimal, but it's pretty clear to see that that's about -0.25, which is equal to -1/4. So we can use our calculator to help us out. So to give you a chance to practice that notation, we'll do a few more using our calculator to find the derivative at that specific value. So again, just to run through it, I'm going to do Math 8. My independent variable is going to be x. My function is x cubed, and I'm finding the derivative at 2. Okay, so we would say our derivative, f prime of 2, is equal to 12. Okay, again, just practicing how to input this, Math 8. Type in my function. And if I want f prime of 3, right, that's telling me to find the value of the derivative when x equals 3. So that's what I'm going to type in here, and we get a value of 2. Now, we can also use this same function in our calculator to actually graph derivatives of a function. So that's what we're going to do now, and there's one difference that I'll point out when we're graphing. So the first derivative we want to graph is the derivative of f of x equals 2x. So I'm going to go into my y equals. Again, I'm going to do math 8. So you can see I get that same notation. So again, my independent variable is x. My function is 2x. But now, I don't want to just graph the derivative at a single point. I want to graph this derivative for all x. So I'm just going to type in x into that spot. If I type in a number, it's just going to plot the derivative at that point. And so when I hit graph, I have to change my zoom. Do that in a second. Zoom 6. And I can see I get that constant function. So again, just to go over that notation, right, you're going to do y equals derivative with respect to x of 2x when x equals x. And we get something like this. So looking at that graph, it's pretty easy to say, my guess would be that my derivative for x, f prime of x, is equal to 2 because it's a constant derivative. Okay, so we're going to practice graphing these using the calculator. All right, again, and we'll just do one more. If I clear this, again, it's math 8, derivative with respect to x. This time I'm doing the natural log of x. And again, I'm doing when x is equal to x. And I'm going to graph that and just sketch what I get. So it looks like something like this is f prime of x. And I'll label this one as well. So we won't often use this functionality, but it's always good to have as a check as we move through the chapter. Now, it's always nice to have these things that we can do on the calculator, but I'm going to warn you there are times where you have to be a little bit careful. Okay? And so here's what we want to look at. It says, using what you know about derivatives and when they do and do not exist, do you think that f prime of 0 exists if f of x equals the absolute value of x? Right? So what this is asking is f of x equals the absolute value of x differentiable? Does that derivative exist? Is it differentiable at x equals 0? And hopefully by now we'd say, well, since that's an absolute value, I know that it's not differentiable there because it has a corner at x equals 0. So f prime of 0, we would say, does not exist because there's a corner at x equals 0. Corner at x equals 0. Okay, well, let's see what our calculator has to say about that. So I'm going to go here again. I'm going to use my nderiv, my math 8. Derivative with respect to x of, let's try that again, of the absolute value of x when x equals 0. And our calculator is going to tell us that that value is 0, which we know is wrong. Right? So the big takeaway here is to make sure you use your brain first and your calculator second. Right? Just because your calculator says it is 0 does not, unfortunately, mean that it's true. We first have to take into account the characteristics of that function that we already know from the behavior of the graph. So that's just a bit of a word of caution there. Okay, so there's one more piece to this that we're going to do. So I'll flip the page. Okay, I've mentioned this a bit, I believe, in yesterday's notes. And so we want to connect up this idea of differentiability and continuity. And so we already know, we've said that a function cannot be differentiable at a point if it's discontinuous at that point. So we're just extending that or formalizing that a bit, I guess. And we want to say if a is a function f has a derivative at x equals a, so if a function f has a derivative at x equals a, then we also know that f is continuous at x equals a. So if it has a derivative, if it's differentiable at that point, it also must be continuous at that point. So you may see a question that says something like number 1. So suppose that we know that f prime of 2 equals 7. Okay, so this is implying here that f is differentiable at 7, or that the derivative exists at 7. So if we know that f prime of 2 equals 7, then we can also say that at x equals 2, f must be continuous. So if we know it's differentiable, we can say that f is continuous at x equals 2. So the big idea here is that if we're differentiable, that implies that the function is also continuous at that point. And I want to caution you that this does not work the other way. Just because a function is continuous does not mean necessarily that it's differentiable. We know that we could have absolute value of x, which is continuous. However, because of that corner, it's not differentiable. Okay, so the last piece. Now we have our intermediate value theorem, everybody's favorite from last chapter. Right? Now we have the intermediate value theorem for derivatives. And it's pretty similar. Now we're just relating it to derivatives. So the whole idea here is that if a and b are any 2 points in an interval on which f is differentiable, so my condition here is that f is differentiable, then we could say that f prime, right, the derivative, takes on every value between f prime of a and f prime of b. So that derivative takes on every value between the derivatives of f prime of a and f prime of b. So this works very similar to the IVT that we worked with in the last chapter. So again, this is an existence theorem. It's asking us if we can guarantee where that value occurs. It's not asking us where to find it. So the first question we have, and we'll actually just do one, and then that'll be the end for today, wants to ask if we can guarantee that f prime of x equals 2 on the interval from 0 to 3 if f of x equals x squared. Right, and we'll just worry about that first interval. Okay, so can I guarantee that f prime of x equals 2 on the interval from 0 to 3? So if my function is x squared, the first thing I need to decide is if I'm even differentiable on the interval from 0 to 3. And since we don't have any discontinuities, cusps, corners, or vertical tangents, we do know that we're differentiable on 0, 3. So we've met that first criteria. So now we need to decide, we need to be able to find the values of f prime of 0 and f prime of 3. And if 2 falls in between those values, then we know that the derivative takes on the value of 2 at some point. So since ultimately I need to find 2 separate values for that derivative, I'm going to use my general formula for finding a derivative, and then I can just plug the 2 values in. So I want to find f prime of x, and my general formula, I know I want to find the limit as h approaches 0 of f of x plus h minus f of x over h. So for our function, it's x squared. We know we have x plus h quantity squared minus x squared over h. So I'm going to work through the algebra here. And if I simplify, I know that's 2x plus h. So now I know my derivative is the limit as h approaches 0 of 2x plus h, which is just 2x. So now I have my general derivative. So it's easy for me to plug in now. If I want to find f prime of 0, I plug into my general derivative, and I know that's 0. And I'll do the same at 3. So f prime of 3, I plug in, and I get 6. So now I already knew that I was differentiable on that interval. Now I can see that 2 falls in between 0 and 6. So now I know by the IVT for derivatives, I can guarantee that the derivative takes on the value 2 in that interval. So a lot of this wording might sound familiar. Now my condition, we said since f of x is differentiable, that's my condition. I have to be differentiable on my interval. And we know our value 2 is in between f prime of 0 and f prime of 3. There's my two conditions. We can say that by, I'm going to say the IVT for derivatives there exists a value c in that interval such that f prime of c is equal to 2. We're guaranteeing that the derivative takes on the value of 2 in that interval. So again, just like IVT in Chapter 2, this is just something you're going to have to memorize as far as the formatting of that answer. The nice thing is that they're very similar in their structure. So tomorrow you'll get a chance to practice all the material from these first two sections. That's it for today.